Hello everyone. Welcome to First Online University, a global platform for all your education and growth related needs. In this lecture, we are going to start with a new topic that is aromatic hydrocarbons, and particularly we will be focusing on the introduction and structure of some aromatic hydrocarbons for a start. Before we begin, a piece of information for you. You can use the coupon codes Mission JEE or Mission NEET while you enroll at First Online University for Mission JEE or NEET. Now let us start talking about the introduction and structure of some aromatic hydrocarbons. Now first of all, it is important for us to understand what does the word aromatic means. The word aromatic has been derived from the word aroma, which is a Greek word meaning pleasant smelling. So anything that has got a pleasant smell, we say that it has got an aroma. So aromatic hydrocarbons are also known as arenes. Now benzene and the compounds that resemble the structure of benzene basically in terms of their chemical behavior also are termed as aromatic compounds. For example, if you talk of benzene, its structure is this, where you have a cyclohexane having conjugated double bonds. Benzene looks somewhat like this. The next aromatic compound is naphthalene, which has got two cyclohexane rings with conjugated double bonds. So there are 10 pi electrons. In benzene, we have 6 pi electrons. In naphthalene, we have 10 pi electrons. That is 5 double bonds alternating to each other. This is how naphthalene balls look like. The next aromatic compound that we have is anthracene, and anthracene has 3 cyclohexane rings with conjugated double bonds. So if you can count, it has a total of 1, 2, 3, 4, 5, 6, 7. So 7 pi bonds, therefore a total of 14 pi electrons. Anthracene looks like this. And lastly, we have furan, which has a 5-membered ring with oxygen as heteroatom present in that 5-membered ring. And again, there are 2 double bonds present. That is a total of 4 pi electrons. Now you will say, how does this become an aromatic compound? We will study what are the rules that make a compound become aromatic. And only if those rules are satisfied in case of certain compounds, then only we call those compounds as being aromatic. Here, the oxygen lone pair has a very important role to play in making furan an aromatic compound. Furan has been used to treat bacterial fish disease as well. And we have thiophene, which is nothing but very similar to furan, but instead of oxygen, we have sulfur as the heteroatom. The entire structure remains the same. The involvement of lone pair remains the same. Just the difference arises in the, contribution of the lone pair in making the ring aromatic, because oxygen being more electronegative is quite resistant to give its lone pair to make this ring aromatic, whereas in case of sulfur, the lone pair is donated easily. So that is the only difference that lies in the chemical reactivity. I mean, that is what is going to bring the differences in the chemical reactivity of the two compounds. And these are the various colors that you see. These are the various forms of, like, at different stages with different chemical properties are thiophene. Other examples of aromatic compounds include caffeine. Now, caffeine, as you must have seen, is present in coffee. It is present in your soft drinks also. It is even present in some green teas. It's present in tea, of course. So if you look at caffeine, these are cocoa seeds only, and from cocoa seeds, coffee is made, and caffeine is present in these cocoa seeds. Now, that is cocoa seeds basically. Next is methyl salicylate is also an example of an aromatic compound. So it is like we are now looking at those aromatic compounds which have got uses in our daily life. Now, methyl salicylate, we will see what it is called in common terms, but it's a pain relieving ointment. If you must have noticed this bottle, the balm that you commonly call it as, it's being used for pain relieving ointment, as pain relieving ointment. Now let us start talking about, so this was just a brief introduction about the various aromatic compounds that we are going to discuss and their structures that we have talked of. Now we will be starting our discussions on the structure of benzene in a detailed manner. So in 1865, German chemist Friedrich August Kekulé proposed the structure of benzene. As we know, there are two different forms, two resonating structures of benzene, which are called the Kekulé form of benzene. So he was the scientist who gave the structure which has been shown in this ring, where benzene has 6 carbon atoms in a cyclic manner, and one hydrogen atom is attached to each of these 6 carbon atoms with the double bonds present as alternating to the single bond. So we call it as conjugated double bonded system. The structure of benzene consists of a cyclic structure with 3 conjugated double bonds, and they are systematically called as 1,3,5 cyclohexatriene. So we have talked of hexadiene, we have talked of alkadiene, alkatriene. So this is nothing but hexatriene only. So here we have 1,3,5 cyclohexatriene. Now, all the carbon atoms that are present in benzene ring have got an sp2 hybridization because they have a single bond and a double bond attached to them, 2 single and 1 double bond. Therefore, sp2 hybridization, the bond angle between one hydrogen carbon and the other carbon is 120 degree. So, if you look at this structure, this is one resonating structure. The other possibility is where the double bonds can shift to the other positions. So, these are the two resonating forms of benzene, and the hybrid form is written as this, with a circle in between the cyclohexane ring. Now, the next thing that we need to look at is the rules, that is the criteria for aromaticity. What are the rules which, when satisfied, only then the compound will be called an aromatic compound? So these rules include, number one, the compound has to be cyclic. Remember, there are 4 rules, and all of these 4 rules have to be satisfied for any compound to be called as aromatic. The first rule is that the compound should be cyclic in nature, that is, should not be a linear chain, whether branched or not, does not make a difference. It should be cyclic. Secondly, it should be planar. And when does planarity come into picture? When we have 120-degree bond angles, that is sp2 hybridized. All the atoms should be sp2 hybridized, all the atoms of this cyclic system. We are not talking about the hydrogen atoms that are outside the ring. We are only talking about the atoms that are present inside the ring. That is, they are part of the ring, should be sp2 hybridized. Then only the molecule is going to be planar. So that's the second condition. The first condition is the molecule should be cyclic. The second condition is molecule should be planar. The third condition is that the system should be completely conjugated. Means there should be alternate single and double bonds present in the cyclic planar molecule. The fourth condition is that the Huckel's rule, that is 4n plus 2 pi electron rule, should be satisfied. Now, what does this mean? If I put n is equals to 1, I will get 4 into 1 plus 2, that is 6 pi electrons. These are present in benzene. Benzene has 6 pi electrons, and therefore, also it is cyclic, it is planar, and it is completely conjugated. So, benzene is an aromatic compound. We will have a look. So as I told you, why was I calculating the number of electrons while I was telling you the structures of these aromatic compounds, was because of this reason. Now if I have a look at naphthalene, naphthalene has 10 pi electrons. So check whether for n is equals to 2 value, there are 10 pi electrons or not. Yes, they are. Plus, naphthalene is cyclic. All the atoms have sp2 hybridization. It's completely conjugated. Therefore, we can call naphthalene to be an aromatic compound. Then we talked of anthracene, which had 7 pi bonds or 14 pi electrons. Now here, put n is equals to 3. So 4 into 3 is 12 plus 2 equal to 14 pi electrons. So anthracene also satisfies the Huckel's rule, and therefore, and also it is cyclic, planar, and conjugated. Therefore, it is an aromatic compound. So all these four conditions must be satisfied by any molecule to be called as aromatic. N can have values varying from 0 up till a very large number. So if we talk about benzene, benzene has a cyclic structure. It is planar because all the carbon atoms, 6 carbon atoms, are sp2 hybridized. It is completely conjugated, that is, it has alternating single and double bonds, and it has 4n plus 2 pi electrons where n is equals to 1. So these 6 pi electrons and all these conditions, cyclic, planar, aromatic, cyclic, planar, completely conjugated, and the presence of 6 pi electrons makes benzene an aromatic compound. The next structure that we have is that of pyrrole. Now, if you try to calculate only the two double bonds that are present, that is 2 pi bonds, so that means a total of 4 pi electrons, you will say that here my n value, any n value, will not satisfy the condition, because here, and still we call pyrrole to be an aromatic compound. Now, what is the reason is that here the lone pair of nitrogen is also taking part to make this pyrrole molecule aromatic. Now, how is it taking part is, it is basically getting involved in conjugation. So here, if you look at this lone pair, it will shift here, this double bond shifts here, this double bond shifts here. So then in that case, nitrogen although gets a positive charge, but the entire molecule will have 6 pi electrons. So here we have 4 pi electrons coming from the two double bonds and 2 electrons from the nitrogen lone pair. So it satisfies the Huckel's rule. Plus it is cyclic, planar, and conjugated. So here it is cyclic, planar, completely conjugated, and 4n plus 2 electrons for n is equals to 1 gives a value of 6 pi electrons, so it is also aromatic. The next structure is cyclobutadiene. Now there is no heteroatom that can donate a lone pair of electrons. So although it is cyclic with planarity present because all the 4 carbon atoms are sp2 hybridized, it is completely conjugated also. But 4n plus 2 pi electrons are not present. Therefore, it is not aromatic. We call it non-aromatic. Okay. So as of now, we have studied two types of compounds. One is aromatic, the other is non-aromatic. A third category is also there, which is called anti-aromatic. Now, let us take the example of 1,3-butadiene. The very first condition of it being cyclic is not satisfied. So it is non-cyclic, although planar, completely conjugated, but 4n plus 2 pi electrons are not present. Therefore, it satisfies only two conditions, and therefore it is not going to be an aromatic compound. So again, we call it as non-aromatic. Now, let us see how we classify the aromatic compounds. If we look at the classification of aromatic compounds, the first classification involves the division of the aromatic compounds into benzenoids. What are benzenoids? Benzenoids are basically compounds that are going to contain benzene rings, one or more. And then if we look at the example, benzene is a benzenoid compound. Benzaldehyde is a benzenoid compound because it has a benzene ring. The second classification is into non-benzenoid compounds, that is those which do not contain any benzene ring in their structure. For example, if I talk of furan, that is this structure, there is no benzene ring present. So it's an aromatic compound, but it is non-benzenoid. Thiophene, similarly, is non-benzenoid. Pyridine is non-benzenoid. Now you will see that somewhere the structure of pyridine matches with that of benzene, but exact benzene ring should be present in the structure for any compound to be called as a benzenoid aromatic compound. Whereas in pyridine, we have a nitrogen present in place of carbon, and therefore this is not a benzene ring, and therefore we do not call it as a benzenoid aromatic compound. We call it as non-benzenoid aromatic compound. Now, what are the differences between aromatic and aliphatic compounds? We will just look at some of the common differences that you should be knowing. The first one is that aromatic compounds always contain higher percentage of carbon as compared to aliphatic compounds. The aliphatic compounds contain lower percentage of carbon. The second is that aromatic compounds burn with a sooty flame. Black sooty flame is what they burn with. Whereas the aliphatic compounds burn with a non-sooty flame. They do not give, black colored ashes that fly in air. Third is that cyclic compounds with alternate single or double bonds are classified as aromatic compounds, and aliphatic compounds, on the other hand, are open chain compounds. Aromatic compounds prefer substitution reactions, where we have one or more of the substituents getting replaced by some other substituent, whereas aliphatic compounds like alkanes, they try to undergo substitution reaction, and alkenes and alkynes, because of the presence of multiple bonds, try to undergo addition reaction, where two atoms are going to be added to each of the carbon atom containing a multiple bond between them, and that is what we call as addition reaction. We have talked about it in detail when we were talking about alkenes and alkynes. Now, this is all about the basic introduction and structure of some aromatic compounds. You can subscribe to our YouTube channel for joining YouTube live classes for best NEET or JEE coaching. You can also download the First Online University mobile app for continuous learning through your smartphones. Keep learning with First Online University, a team of millions of learners and educators worldwide.